homework set number 2, section 5.2. Okay, so the problem originally states set of conditions and statements, and says that dry air moves upward, and in doing so it expands at a rate of 1 degree for every 100 meters rise, up until about 12 kilometers. So if the ground temperature is 19 degrees, we know what is our initial, well, let's use terms of temperature. Our initial temperature is 19 degrees Celsius. And that is at ground level. So we know our position. Let's state position as X. Initial is 0 meters, right? And then it asks for a formula. Well, first the facts. For every 100 meters that I change upwards, or that I rise, I change 1 degree Celsius. So my change in X is 100 meters, and my change in Y is 1 Celsius. This is true only when it is given as a linear proportion, or a linear rate of change. So we can state that our slope, or our rate of change, is our change in Y over our change in X. This is the same formula you've been using on previous years for determining the point slope formula. And this is the same thing as saying your final Y minus your initial Y over your final X minus your initial X, right? Okay, I want you to express in terms of delta Y, delta X, just because it is important that you start to use mathematical interval notation. So from here, we know that our slope, if, let's analyze the problem first. If the temperature at ground level is 19 degrees, when we are at ground level, saying this, my x-axis is in meters, and my y-axis it is in temperature, or I mean in degrees Celsius. We call this T, our temperature, and our position in meters. Then when we are at ground level, our temperature is 19 degrees. Let's call this 19 degrees Celsius. So that's our starting point, right? That's given, which is 0, 19, right? And then it states that I'm going to change at a steady rate of 1 degree Celsius for every 100 meters I move on my graph, right? That makes it works. All right. So then it tells us that this change is only true for any value of X within 0 and 12 kilometers. That's given, right? It says, as dry air moves upward, it expands at a rate of 1 degree Celsius for every 100 meters rise, up to 12 kilometers. So that means that the air is gonna keep cooling down. It's gonna keep cooling down until we reach 12 kilometers. If this was our graph, then until it reaches 12 kilometers, then we do not know what happens further on, right? So my problem is only defined in this interval or domain, right? Okay, so this is our given initial interval, which we can express as an interval notation, which is 0, 12, right? This is my domain, because it is all the values or set of values that are defined within the statement. Okay, so that means that I am only able to determine a temperature at, let's call this kilometers, just to not work with big numbers. Okay, so 12 kilometers, 19 degrees. And it says that my rate of change is that I go down 1 degree Celsius. I go down 1 degree Celsius for every 100 meters that I move upwards. This is an absolute value in height, because when you jump 1 meter, you say I jump 1 meter and I come down 1 meter. No, not I jumped 1 meter and then I come down -1 meter, right? So you express this in absolute value, but it's better to express it as a magnitude. It's called magnitude. Okay, so when I am at 12 kilometers, I don't know how the graph will behave. I don't know if it'll be down here or if it'll be here, I don't know, but I can only define this statement from 0 to 12. Okay, so I have determined that my slope, or the rate of change at which the function behaves or will be defined, is -0.01, right, degrees Celsius per meter. This is slope. This is the slope. Don't get confused with meters. Okay. And if we apply the formulas and the knowledge that you've been acquiring from previous problems, we can state that if the formula mx plus b, or the point slope formula, which is defined by the arrangement of these variables onto this point, we can already know that my rate of change, or my slope, is -0.01, and that my v is 19 degrees, right? Because whatever happens to my function is gonna change from this point on. So 19 plus something plus minus something, that's gonna give us the behavior of the graph, right? So if this is 0 and this is 9, at 0 it is 19, what will be my temperature when I am at a height of 12 kilometers? So I can further state that this is an independent variable that will cause y to change, and we call this a function. So as my x changes, this value changes in function of x. Okay, so if we replace values, or better said, if we use the data that we have determined for solving such problem. Sorry, let me get this. We can say -0.01 degrees Celsius per meter times my final, or my value for x, for which I know it will stop expanding, or expanding at a different rate, not this rate anymore. That is 12 kilometers. careful here. This is meters. If we express this as meters, we have to express this as meters as well. So 12 kilometers times 100 meters, 1 kilometer. Okay, so this is, and we get meters, which we can further work out at negative 0.01 degrees Celsius over a meter times 12,000 meters plus 19 degrees Celsius, which is the original or the given value for temperature. So this, if this is position, then this is my position, and my temperature in function of my point in time, which is x. So careful here with the notation. I just made this to make it clearer for you, because you're going to be dealing a lot with the function notation. But this will tell you your value in degrees. And how do you know that? Because if you start dealing with units, you have to have the same units enabled to get a value here. So I know this is going to be expressed in degrees Celsius. Okay, so I just go ahead and convert, and I get that the temperature in degrees Celsius at 12,000 meters is going to be 0.01 times this, which is going to give me a value of 12 per meter, right? So that is my temperature at 12 kilometers or 12,000 meters, right? Now, if we move on, I'm just gonna move forward to the next page. So at 12 kilometers, my temperature is, careful here, meters cancels out with meters, and we get only the temperature has to be expressed in degrees Celsius. So my temperature at 12 kilometers equals negative 12 degrees Celsius. All right, so negative 12 degrees Celsius. Now, we go back to the original problem, which states what is the, give a formula for the temperature in degrees Celsius, in Celsius degrees, at any height x. So I already know the value at this point, which is true for any x. So if the temperature, let's just express in variables without the units, is given by negative 0.01 times x, which is my height, plus 19, I already have a value for x, and I already have defined my domain and my range. My domain is 0, 12, because this is the, and when it is 12, I have a value of 12, and when it is 0, I have a value of 19, right? So the temperature needs to be the formula needs to be expressed as formula at any given height x. So the temperature further on can be expressed as negative 19 plus T equals negative 0.01 x. So my x, I'm just changing sides here, equals T minus 19 over negative 0.01. So this is the same as saying x is defined negative T 0.01 plus 19 of 0.01 should be 0.19 if I'm not mistaken, right? So I say at 100 meters my temperature is something over 0.01 plus 0.19. So if we are at x equals 0, which is the initial condition, 0, we have negative, and my T is 19.01 plus 19, so 0 equals 0. So we have proven that this is a formula that expresses any point, any temperature at the temperature at any given point x. So if you want a formula for knowing what is the temperature at any given point x, then you must say that there's a couple of ways of writing it. As a function of x, and this is defined here, 0.01 x plus 19. That's when my x changes, my value changes in function of x. Then obviously there's this as a mathematical point slope notation, or equation of a line, negative 0.01 x plus 19. And we also have the way expressing it as a formula, and a formula is your initial temperature, or your y, in this case we're using T, minus 19 over negative 0.01. And this can be expressed as this, as this, right here. So we can express it as negative T over 0.01 plus 0.19. This is a formula, which a formula states no equation. The formula states just a set of operations that throw out a value. The formula to getting degrees Celsius, you know that you just do whatever value over whatever value plus whatever value, you get that. That's the formula. When you use an equation, then you must set a dependent variable. So this is your solution for that problem. And also it says what is the range that you can expect when you are at kilometer 10. So that means undefined from here to here. This is not a scale, but we're going at a very, very shallow, not steep slope. So what is the range I can expect when I'm here? So I just want to know the distance from here to here, and this is the range in temperature that I can expect to have. So using my formula, if I want to know this temperature, I just have to go back to my original problem, and the temperature is expressed here. So temperature equals negative 0.01 x plus 19. So my temperature at this given point equals negative 0.01 times 10 kilometers. Careful, we are expressing in meters, so we have to change this to kilometers, and plus 19 degrees Celsius. This is in degrees Celsius per meter, and our temperature there will give us that we are negative 10, right? Negative 100 plus 19. So our temperature there has to be negative 81 degrees Celsius. Careful there, just if it's I can expect from here to here. When at 10 kilometers is the distance from here to here. So this is my range at 10 kilometers. And if I have this point, which is negative 81 and 19, I can express it as negative 81 and 19. That's about it.